Okay, once again, picking up where we left off in the first segment, we have another example of finding velocity functions. If an object has a position function that's given by this equation here, that is r, vector r, as a function of time, is 10t minus t squared I plus 5tj plus 5tk, what is its velocity function? Well, velocity is, again, a derivative of position. So you take the derivative of this equation that we just went over, and we find that for the 10t term, the derivative is going to be 1, because t is to the first power here, 1 times 10 times t to the 1 minus 1 power, which is what we get here, minus 2 times t to the 2 minus 1 power, and that's times the unit vector I, plus 5, let's see, we've got 5t, so that's to the first power, true, and so is that. So that's going to be 1 times 5 times t to the 1 minus 1, okay, times j, and the same thing for k, unit vector k. So cleaning this up and consolidating our terms, we end up with 10 minus 2t times unit vector I plus 5j plus 5k. And so that is the velocity function. Okay. Yeah, I wrote it again to clean it up a little bit, make it look nicer, but this is essentially the same as what I had written up here. So it's 10 minus 2t times I plus 5j plus 5k. Okay, if it also wants to know what is the acceleration function. Well, for the acceleration function, you take the derivative of the velocity, which is what we just had here. So you take the derivative of this now. 10 by itself, just the number, is again equivalent to being 10 times t to the 0. So you would multiply the coefficient by the power, which is 0, and the entire term becomes 0. So again, the derivative of just a number with no variable attached to it is 0, minus the derivative of 2t. T is now to the first power. So that's going to be 1 times 2 to the 1 minus 1 power times I. And then for j, again, 5 is just a number, no variable attached to it. So the derivative of that is going to be a 0 times 5. And the same with the k term, 0 times 5, and that zeroes them out. And so the only thing we end up left with is negative 2, and then t is to the 0 power, so that disappears because that's 1. And so it's just negative 2I. That is the acceleration vector. Okay, and then it asks you to describe the motion from t equals 0. And to do that, you can actually look at the equations and try to deduce what they mean, or you could just slip in some values like 1 second, 2 seconds, 3 seconds, and so on for the time in both the velocity and the acceleration equations, and find out what the particle or object is actually doing at those times. And when we do that, we find out that the volume or velocity, decreases in the x direction with constant acceleration until 5 seconds, at which point it changes directions and accelerates in that direction, goes faster and faster in that direction. Because after 5 seconds, the acceleration, the acceleration is negative. And so once the object changes directions, it will be going faster and faster in the opposite, the new direction. Since there are no, since the y and z terms in the velocity equation are just numbers, with no variables attached to them, you can say that the velocity in the y and z directions is constant. And that's basically also confirmed when you look at the acceleration equation and notice that there are no y or z terms at all in the acceleration equation, meaning the acceleration in the y and z directions must be zero, and zero acceleration is just another way of saying constant velocity. Okay, so that makes sense. In cases where the acceleration is constant, things become a little bit easier because you can essentially use the same equations that we used in previous chapters for one-dimensional problems for things like position and velocity and let's see, and that sort of thing. So the only complication really is that now we're dealing with 2 or even 3 dimensions. But that's not as complicated as it might seem, despite this wall of equations here, because if you'll notice, these here in the first column under x are the equations that we've been pretty much used to all along, dealing with to find things like position or velocity. So position in terms of x as a function of time would just be the original position times the velocity, average velocity in the x direction times t. That's pretty much the same equation that we used before. It was just x final equals x original plus vt. So this is just a little small variation on that. For velocity as in the x direction as a function of time, it's the original velocity in the x direction plus the acceleration in the x direction times time. And that is very similar to the equation that we've been using for that in one dimension. You can find the position as in the x direction as a function of time also by taking taking the original x position and adding to it the velocity, the original velocity in x direction times time, plus 1/2 times the acceleration in the x direction times time squared. And again, that equation should look pretty familiar. And also we can find the velocity squared in the x direction as a function of time just by taking the original velocity in the x direction plus 2 times the acceleration in the x direction times the displacement in the x direction, which again looks very familiar. If you examine these other equations for the y and z direction, I started running out of room here, so I had to squeeze things in. So in the book, they give you the equations for the y direction written out, and you'll notice that if you look at them, these equations for the y direction are all exactly the same as the equations for the x direction, except all the x's have been replaced with y's. So you use the same equations. It's just, y replaces the x. And it's also true, although the book doesn't give them, it's also true that the similar equations for the z direction are also identical to this first batch of equations, except in that case, all of the x's will be replaced with z's. So position x as a function of time equals xo plus vx average times t. Well, position z as a function of time equals z original plus vz average times t. So again, the equations for the 3 different directions are all the same. It's just that you use the direction x, y, or z. Okay, the position equation for something as a function of time, again, can be given in 3 dimensions by the x position as a function of time times unit vector I, plus the y position as a function of time times unit vector j, plus the z position as a function of time times unit vector k. If this is a two-dimensional situation, then just leave out that last term involving z. The velocity vector as a function of time can be thought of as the velocity in the x direction as a function of time times unit vector I, plus the velocity vector, or velocity, sorry, in the y direction time as a function of times j, plus the velocity in the z direction as a function of time times k. And again, if it's two-dimensional instead of three, just leave out that last term. Okay, we can look at an example of movement that's occurring in two different directions at the same time by considering the case of a skier who's going downhill. And I've drawn a very crude diagram here. There's a much prettier one in the book if you want to look at it, of a skier who is skiing downhill from the lodge, and the hill itself is at an angle of 15 degrees to level ground. And so the skier is moving downhill with an acceleration of 2.1 meters per second squared, downhill at an angle of 15 degrees. And so there's your angle there. The acceleration, because it's at an angle, this acceleration is a magnitude of an acceleration, basically going downhill in this direction. And the origin is considered to be the front of the lodge. That's the little house I drew here. And the initial position of the skier is given by the vector r at 0 time, and that is 75.0 I. And that means that the skier is 75 meters in the positive direction, which we're defining as being to the right, like we usually do. So 75 meters to the right in the x direction from the lodge, and minus 50j. So the skier is actually 50 meters downhill in the y direction from the lodge. That doesn't mean that this distance here is 50 meters or 75 meters even. 75 meters is the x term. So basically this distance here horizontally, that's 75 meters. And this distance here, or say, I guess this distance here, it's kind of small to see, but this distance here would be 50 meters down in the y direction. Okay, the initial velocity is given by velocity vector at time 0 is equal to 4.1 I minus 1.1 j. That just means that the skier is going 4.1 meters per second in the x direction and downward at 1.1 meter per second in the y direction. And so the question is asking, first of all, what are the x and y components of the skier's position as a function of time? To use that, or to find that out, we're going to use the equation x final equals x original plus v original in the x direction times time plus 1/2 acceleration in the x direction times time squared for the x direction. And then we'll use the analogous equation for the y direction, in which all of the x's are replaced by y's. So that would be y final equals y original plus v original in the y direction times time plus 1/2 a y t squared. But if you look at what we've got here in this equation, we know everything actually in both x and y terms, well, except for x final. And we don't know the acceleration in the x and y directions. We know velocity, we don't know acceleration. So first we're going to have to find the acceleration in the x and y directions. Since the skier is on a slope, acceleration in the x direction is going to be the magnitude of the acceleration in the x direction times cosine theta, 15 degrees being theta. In the x direction, the skier is picking up speed going in the x direction. So that would be 2.1 meters per second squared times cosine of 15, which is 0.966 times 2.1, which is 2.03 meters per second squared. That's your acceleration in the x direction. In the y direction, the skier is headed downhill, so that 2.1 meters per second for the magnitude, or sort of the magnitude in the, the acceleration in the y direction, for A, you would use negative 2.1 meters per second squared because the skier is going downhill. Times, and that's going to be times the sine of 15 degrees. Okay, so A sine theta. So that'll be end up being negative 0.544 meters per second squared, and that's acceleration in the y direction. So now we have all the stuff we need to find the equation. So x final, or x position at any given time, is going to be x original plus v original in the x direction times time plus 1/2 acceleration in the x direction times time squared. We now have all of that information. X original, the original position in the x direction was, 75 meters. Okay. V original in the x direction was 4.1 meters per second. And that's going to be times the time, because we haven't dealt with specific times yet. So that'll be just times time. Plus 1/2 the acceleration, in the x direction, which is 2.03. I just use it as 2.0 here, meters per second squared, times time squared. And so that is the equation for the position in the x direction at any given time. For y, we used, again, the same equation, only all of the x's are replaced with y's. So the y position at any given time should be y original plus the original velocity in the y direction times time, plus 1/2 the acceleration in the y direction times time squared. But you got to remember, you're not using the same numbers you used for the x direction, because x and y are independent of each other. So the original position in the y direction comes from the initial position equation, negative 50 meters, plus the original velocity in the y direction comes from the initial velocity equation, which is negative 1.1 times time, plus 1/2 of the acceleration in the y direction, which is negative 0.544. I almost wrote in 2.1, but it's a negative 0.544, times t squared. And so your equation for the position in the y direction at any given time would be negative 50 meters minus 1.1 meters per second times time, minus 1/2 0.54 meters per second squared times time squared. So there's your equation for the y position at any given moment. For velocity, we can use the equation of final velocity, or velocity at any given time, is equal to the original velocity plus at. So for the x direction, it's going to be the velocity at any given time in the x direction is equal to the original velocity in the x direction plus acceleration in the x direction times time. And some of these numbers we know, so we can put them in. The original velocity in the x direction was 4.1 meters per second. So we can put that in for VOX. And the acceleration in the x direction was 2.03 meters per second squared. So we can put that in for acceleration. So the overall equation for the velocity in the x direction at any given moment would be 4.1 meters per second plus 2.03 meters per second squared times time. And overall, that would give you units of meters per second. Sorry, for the velocity in the y direction, you use the analogous equation for the y direction. So the velocity at any given time in the y direction would be equal to the original velocity in the y direction plus the acceleration in the y direction times time. So for the y direction, we have the initial or original velocity was minus 1.1 meters per second from here, plus negative 0.544 meters per second squared from here, times time. And there is your equation for finding the velocity in the y direction. Okay, the question then goes on to ask specific questions, like what are the position and velocity at 10 seconds? What that means is you just come back to the equations that we had for position and velocity, and anywhere you see t, just insert 10. So if the position in the x direction is given by 75 plus 4.1 times time, that's going to be 4.1 times 10, or 41, plus 1/2 times 2 times t squared. Well, that's going to be 1/2 times 2 times 100, or in other words, 100. So all of that adds up to 216 meters. So that's how far the skier is away from the lodge in the horizontal direction at 10 seconds. And in the y direction, the distance that the skier is from the lodge is going to be given by this position here. Minus 50 meters minus 1.1 times time, which is 10, minus 1/2 0.54 times 10 squared. So that comes out to negative 88 meters. Okay, if you wanted to know the question didn't ask it, but if you really wanted to know the distance downhill, we could basically, what you're doing here is taking the hypotenuse of a right triangle. So the distance the skier is down the hill is just basically c squared equals a squared plus b squared. Or in other words, c is the square root of a squared plus b squared. And so there's a and there's b. So it's going to be square root of 216 squared plus negative 88 squared. And if we actually try doing that, 216 squared is a really big number, plus 88 squared equals an even bigger number, but take the square root of that and you get 233 meters downhill from the lodge. Okay, the velocity will be done using the velocity equations from the last page. So we have at 10 seconds, we have the original velocity in the y direction plus the acceleration in the y direction times the time. And that comes out to 24.4 meters per second. And in the y direction, we have velocity in the y direction at 10 seconds is equal to the original velocity in the y direction, that's minus 1.1 meters per second, plus the acceleration in the y direction, that's negative 0.544 meters per second squared, times the time, which is 10. And that comes to negative 6.54 meters per second in the y direction. In vector terms, for the velocity, since that's on this page, the velocity vector equation can be given as 24.4 times unit vector I, because that's in the x direction, minus 6.54 times unit vector j, because that's in the y direction, and that's meters per second. For the position, we can do the vector equation as 216 times unit vector I, because 216 was the position in the x direction. And we can then take that minus 88j, because negative 88 was the position in the y direction. So those can be the, and that's meters. So those would be the vector equations for the position of the skier at 10 seconds. Okay, well, I think that fills up this segment, and we'll start with projectile motion in just a moment.